The simulation steps in my game Steam Revolution consist of a sequence of loops over all trains or industries. The duration of the loops is extremely short, on the order of less than 10 microseconds per loop. Off-the-shelf parallel libraries have too much overhead and actually make the game run slower than single-threaded. So I made custom parallelization primitives that have 1/8 of the overhead of OpenMP in some circumstances. I give an overview of important CPU architecture details that affect the implementation. I describe how I implemented atomics, spin locks, and a parallel for primitive. I then show synthetic benchmarks of how my implementation beats OpenMP and PPL. This video is about computer architecture and how to maximize a computer's potential. I describe primitives that could be used in any program, and how I actually use them to parallelize my game will be shown in a follow-up video. This is going to be an in-depth technical video, so buckle up. This video is about designing and optimizing computer code. If you like optimizing things, then you might like my game about designing and optimizing train routes. Okay, back to the main topic of the video. Before I start talking about the actual code, I need to talk about what the code is going to run on, i.e., a computer. And in this case, a specific computer, which is my computer, but in a more general sense, modern-day x86 computers. All of the timings and benchmarks that I'm going to show are on my actual computer, so let's talk about what that is. It's a Ryzen 2600X. This is a mid-range x86 released in 2018, so that's about 6 years old at the time of this recording. And it has 6 cores. Rather, the 2700X, which it's based on, has 8 cores, but the 2600X is a cut-down version of that has 2 of the cores disabled. Each of the cores is presented to the operating system as 2 logical processors, which I often will refer to as hyperthreading, although that's technically a trademark term of Intel. As you can see from these die shots, there are actually 2 separate clusters of 4 cores each, and they're physically separated from each other. My main problem is that I have extremely short duration workloads, and the main limiting factor for a short workload is the amount of time it takes to distribute that work amongst different cores and to collect the results. Another way of saying this is that I'm limited by the latency of the communication between the different cores. So let's try and take a look at some benchmarks that other people have collected on my processor. Well, technically not my processor, it's the 2700X, because I have just a cut-down version of that. So let's just scratch out a couple of these rows and columns and pretend that that's actually my processor. The most obvious thing that you'll see stand out to you is that there are definitely 2 clusters of cores. Some of the cores have around 20 nanosecond latencies between each other, and other cores have around 90 nanosecond latencies between each other. And this represents cores that are within the same physical location versus across the chip from each other. So if we want to figure out what is the lower limit on the number of clock cycles that will take to communicate between the different cores, we can use the numbers on the graph and look at the minimum latency that was measured. And that was 22.8 nanoseconds, which it says was with a CPU that was clocked at 3.7 gigahertz. This comes out to around 84 cycles. In order for a communication to be useful, oftentimes it needs to be two-way. So that means that a round trip time to send a message and receive a message back is around 169 cycles. This is a theoretical lower bound on how long a parallel job can take, and we'll see if we can achieve it. Another key takeaway that we can get from this graph is that really short duration workloads, in order to have a low enough overhead, need to use fast local cores. And then if we have longer duration workloads that are doing more work, then we can split that across cores that are over the entire chip, because they're not going to be as latency critical. So if we have something that takes, say, a millisecond or longer, we might as well use all of the cores. Of course, that's just my computer. There's other computers that have different layouts and architectures. So let's take a look at something else. Going forward, there's really two main classes of relevant chip layouts. The first is chiplets, at least the way that AMD is using chiplets. So to take a look at a more recent AMD chip that's from the Zen 4 family, here the chip is actually split into multiple physical pieces of silicon that are then stuck together with an interposer, whereas my computer is actually still on the same die. I show latencies here for a Ryzen 9 7950X, which is composed of actually 3 chiplets. 2 of the chiplets contain core clusters. So that's what you see here, is that there's 2 different sets of cores that have distinct latencies from each other. And the third chiplet is containing memory controllers and various other things like that. In terms of programming, this chip actually looks pretty similar to mine, in that there's a set of cores that have really low latency to each other, and then communicating to a different cluster is quite slow. An alternative approach that's taken by Intel is to split up the processor into big cores and little cores. So the big cores are devoted more silicon area, they're given larger caches, and just generally more compute resources to be as fast as possible, but quite power consuming. And then there's little cores, which are physically smaller, take less power, and are not as capable, but aren't intended for running major workloads. They're more for background processing. The concept of little cores is something that is more common in mobile and laptop processors, where a majority of the time the device is idle or sleeping, and you don't need to be powering big cores because there's not really much to do. So you turn off all the big cores and just run some stuff intermittently on the small cores. In terms of programming, what we can see is that the latency for communicating between any of the big cores is pretty similar regardless of which core you're on, but that communicating to the little cores can be significantly slower. Something that's really odd about this graph is that the little cores, for some reason, are slower at communicating with other cores in the same cluster than they are to other cores outside of their cluster. And this is extremely strange. The reporters at AnandTech seem to agree with me that something weird is going on here. I don't really have any insight into this, but what you can see comparing the AnandTech graph versus the graph on the left is that in one it shows the latencies between cores, and in the other it shows latencies between logical processors. And here you can see that the big cores have 2 hyperthreads per core, whereas the little cores have a single hyperthread in a core. Either way, it's clear that this trend of non-uniform memory architectures, where communication between different cores takes different amount of time, and also just the concept of having different types of cores, perhaps in different chips as well, is going to continue. AMD was early to the game with using chiplets, but Intel is basically doing the same type of thing as well now, but they call them tiles instead. The reason that this is going to continue is that using smaller chiplets will give better yields because there's a certain defect rate per area on a silicon wafer. And if you have a smaller chip, then there's a lower chance that one of those defects is in your chip. If you have a bad chip, then you can throw it out. Alternatively, you can sort chips by their quality, and you can take, say, all of the best of your chips and put them together into a premium product and take the worst and put them into a lower end product. So it's really good for product segmentation. Another advantage is that you can effectively, in aggregate, put these chiplets together to make something bigger than you even physically could using a single chip, because there's a limit that's called the reticle limit of how much area you can actually image. Beyond putting chips side by side, there's also going to be a greater prevalence of 3D stacking dies where you put chips actually on top of each other. And as well, it's going to become more and more common to use different levels of manufacturing technology for the different chips. The basic idea is that there are some components of a computer that really need the most up-to-date, smallest lithography technology, whereas other things don't. So, for example, you want really the best lithography for making your CPU cores and your GPU cores, but things like the memory controllers, PCIe controllers, and the level 3 caches can use older technology because those don't scale as well. It also has an advantage of diversifying the supply chain. So you can combine chiplets potentially from different suppliers. An example might be that Intel can use TSMC chips combined with their own chips to make a CPU. Or perhaps in the future, NVIDIA or Qualcomm GPUs could be used with an Intel chip. Who knows? What's also interesting is that because the chips are smaller and potentially more specialized, this opens up a market for smaller companies to make domain-specific chips like, for example, network interfaces or artificial intelligence chips. So that's fine and all, but how do we actually go about choosing the fast clusters of cores versus not? Fortunately, operating systems, and in particular I'm using Windows here, provide some diagnostic information. There's a call that you can make to the OS that will give back a list of all of the cores and what their logical processor masks are, as well as a list of all the caches and what their logical processor masks are. From that, you can try to determine some information about what cores are grouped with what other cores. In order to determine this, we need to know a little bit of something about how the cache hierarchy works on a processor. If your cores are split across different chips, and currently AMD is the only one who does this, but this is a general principle. When your cores are split across different chips, then cores that are close to each other are going to share some caches. Typically, a core will have access to multiple levels of cache, and right now it tends to be 3 different levels of cache, but in the future, who knows, maybe it'll go up to 4. The first level of cache is the L1 cache, and typically this is split into an L1 data cache versus an L1 instruction cache. Basically, the instructions for actually running your program are stored in a separate cache from the data that the program is manipulating. Below that is an L2 cache, which is larger, but still is tending to be just connected to a single core. Below that again is an L3 cache, and this is a cache that's shared among multiple cores and is the level at which the data is communicated between the cores. Finally, there's the actual system RAM, which is actually not part of the CPU at all. There's a memory controller in between, and the RAM is super slow, and we don't really need to worry about it. What you'll notice from my diagram here is that the clusters of cores are sharing an L3 cache, and they don't share the L3 cache from the other cluster. So if you can look at the masks of what is in the same L3 cache, then that probably is telling you what's in your cluster. Intel is a little bit different in that all of their cores share the same L3 cache, but the big processors have hyperthreads, at least in their current generation, and the little ones don't, and so that's another distinguishing feature we can use. So if a core has two logical processors, then we'll consider that to be a fast core. Now that we've discussed how we can identify which cores are which, we should talk about how we can actually communicate between them. This communication is described by what's called the memory model of the computer. This basically describes the set of guarantees that a computer architecture makes about what reads will be seen where and when versus the writes. In general, you should consider that instructions between different processors might be interleaved in any different way. One reason for this is because the operating system is controlling these threads and putting them on the different cores, but it's also having to share your program's processing time with other programs. And it does this through time slicing. So at any arbitrary time, it may take control over a core, throw your thread out, have some other process run, and then at some later time might put your thread back onto the processor, or even onto another processor. This is an entirely unpredictable process and is controlled by something that doesn't understand the internal state of your program either. So that's one source of how reads and writes might happen in an order that you don't quite expect, and is by itself what would be referred to as a sequentially consistent memory model if that was the only thing that affected it. Viewing parallel processing as being sequentially consistent, where the instructions between different processors just happen at arbitrary times, will get you a long way, but it's not the full story. The other aspect that you need to consider is that processors are actually connected by a network on the chip, and reads and writes aren't communicated instantly. It's then an architectural interface choice to decide how much the computer will work to pretend that they do happen instantly. As far as I'm aware, no major modern processor acts as something that's fully sequentially consistent, because that's very difficult and slow to implement. x86 provides one of the stronger memory models, and ARM provides a somewhat weaker memory model. Here I'm going to be focusing on x86 because that's what I have and that's what I'm targeting. In x86, the main weakening of the memory model comes from writes being buffered. This means that other processors may see the writes delayed, but the writes will be guaranteed to appear in correct order, and otherwise things act as if instructions are just interleaved with one another. Although x86 provides a pretty strong memory model, it turns out that actually compilers don't, and because you're writing something in a higher level language like C++, and then that gets compiled down, the optimizations that the compiler will perform can actually result in a weaker memory model. So if you're going to be doing parallel programming, you need to basically assume that you have an extremely weak memory model and program accordingly. Some examples of what I mean are storing data in variables does not mean that they're written to memory. Rather, if a variable is used frequently, then chances are that it's going to be kept in a register and not stored to memory. This then means that that variable is not going to be visible to any other processors unless you explicitly tag it as being volatile, which means that every read has to actually retrieve the value from memory, and every write needs to actually write it to memory. Compiler optimizations will also do all sorts of reordering of instructions, and calling it a reordering might be too weak of a term because it can do bigger manipulations than reordering. But in terms of the memory model, the end effect is that reads and writes might happen in a different order than you had written them in the code in the first place. In order to restrict the types of optimizations that the compiler can do, you can use a read-write barrier, as it's called in Visual Studio. And this is something that acts like a memory fence that would be an instruction in the computer architecture itself. But this acts for the higher level language. What this says is that all read and write operations that happen in code before the fence have to actually stay before the fence, and all read and write operations in code after the fence have to stay after the fence, and the optimizer is not allowed to cross the fence, basically. Another thing to keep in mind is although memory is byte addressable, the smallest unit of a memory transaction is a cache line. And CPUs seem to have stabilized on a cache line being 64 bytes. What this means is that whenever memory is read from one core to another core, the entire cache line is sent. Whenever you read something from RAM, an entire cache line is read, etc. The way that cores resolve conflicts in reads and writes happens at the cache line level. The basic way this happens is through something like the messy protocol, in which cache lines are tagged with a state. They can either be modified, exclusive, shared, or invalid. In order to change the state of a cache line, a core first needs to communicate over a shared bus and get acknowledgement from other cores that it's able to do so. I'm sure there are lots of implementation details about how that works, but from the perspective of a programmer, the basic result is fairly simple. If a bunch of cores are reading data, but none of them are writing it, then that's cheap and there's not much communication overhead because the cache lines will all be in a shared state. If a core wants to write some data, then that's going to have a cost associated with acquiring the cache line in the first place. But if you are the only core writing to that data, then subsequent writes are going to be fast. The real problem comes from if you have multiple different cores that are simultaneously trying to read and write to the same cache line. In that case, they're all going to be trying to check it out and get exclusive locks effectively on it, and that is potentially very slow. Because there's no real explicit control or saying what is in a cache line or not, it's just implicit by if you happen to be in a 64-byte grouping. You need to be careful to avoid what's called false sharing, which is when you put some data that you use to communicate between different cores into the same cache line as other data that is not intended for that purpose, and which can then become very slow to access. This then brings us to hyperthreading, which is when there are multiple logical processors that exist on a single physical core. The way to understand this is that processors execute instructions out of order. What this means is that there's a front end that will decode the instructions in order and then pass them to the back end. The back end will then launch the work on multiple different execution units, or what are called ports. The instructions are tagged with what their sources are and what are the dependencies between the instructions. If there's no dependency between the instructions, then they're free to run in parallel. Otherwise, the dependent instruction needs to wait for the one preceding it to finish. The results of all these executions are then collected into a reorder buffer before being committed. And this is what makes it look like the instructions actually happen in sequence when they didn't at all. A consequence of this type of design is that CPUs tend to over-provision the execution units of any given type. The thing is that there are different types of programs that will run on a CPU. Some use a lot of numerical computations, like scientific computing, for example, whereas others hardly use the floating point unit at all, and they're doing mostly integer and branching and jumping instructions. An example of something like this might be some business software. And then you have a more typical use case, which is programs that are going to use some floating point instructions and some integer instructions, some memory instructions, and a mix of other stuff. In a program like this, the distribution of how the instructions are used is not going to be uniform, though. There's going to be still bursty characteristics where sometimes it uses a lot of floating point, sometimes it uses a lot of integer, and so on. But the CPU needs to be fast in all of those cases, so it has execution units for the worst case scenario of all of the cases. But what that means is that there's a lot of slack resources available. So something that you can do is you add extra decoding and reordering backend parts to the CPU, and that allows you to more fully utilize these execution units. So you can come up with the idea of a logical processor, and then you just tag instructions with what the source processor index was. What's nice about this is that there's guaranteed to be no dependency between instructions from the different processors, and so you are always going to be able to execute those in parallel. This has a net effect of increasing the throughput because you're able to use the slack capacity, but now your threads are competing for resources, which means that they're going to have a higher latency. What's also worth pointing out here is that hyperthreading is really good also for hiding stalls of various sorts, and the main example of this is memory stalls, because it can be very slow to read something from RAM. That's cool and all, I hear you say, but what does it mean to me as a programmer? Well, the key point was about the latency versus throughput. So if we have a situation where we need extremely low latency, such as the goal of this video to make my really short duration parallel work run fast, then we want to make sure not to use hyperthreading. And if you have a workload where there's just a lot of work and you want to have high throughput, but you don't care about the latency, then you want to use the hyperthreads and all of the cores. So that's all of the computer architecture stuff I wanted to talk about before getting into the implementation. If you've liked what you've seen so far, then please consider subscribing to my channel to get future videos. In terms of implementation, there are three things that I'm going to talk about that build up on each other in terms of complexity. The first is an atomic integer, which is the basic primitive through which you can communicate. Second is a spin lock, which is a little bit higher level mechanism for threads to communicate with each other. And finally, parallel for, which is a mechanism for distributing work among different threads. All right, so starting with the atomic integer, one of the first things I want to talk about is how API design affects your implementation and the performance of your implementation. You wouldn't think that there's much API design behind an atomic integer, but it is possible to do it wrong, and so I'm going to, I guess, go into a little bit of a mini rant about the standard template library. In my opinion, the standard atomic is a case study in how you can take something that is actually fairly simple and still manage to mess it up. I think this actually exemplifies a fundamental misconception of what atomics are. The thing is that in the computer architecture, there is no such thing as atomic memory. Instead, there's memory, and then there are atomic operations that can be performed on that memory. However, the standard library thinks of the memory itself as being the atomic object, and so places various restrictions that aren't necessary and make it actually really difficult to use in some situations. The biggest problem is that the standard atomic has the copy constructor explicitly disabled. So you are not able to copy an atomic integer, for example. The result of this is that you can't use an atomic variable inside of a struct that is then in a vector. And here I mean a vector as in a resizable array. The problem is that when a vector is resized, the way it does that is by allocating new memory and then copying the old data into the new memory and deleting the old data. You may have noticed that I used the keyword copy, which is done through the copy constructor. Because that's disabled, no atomics in vectors. This means that if you want to have a fine-grained parallelism where different threads are accessing different elements of an array but not stepping on each other's toes, it's basically impossible to do that with the standard atomic. This is, again, not a limitation of how the computer architecture itself works, but something that's imposed by the design of the atomic API. If you look this up online, people have run into this problem and they propose solutions. And those solutions often look like, oh, why don't you inherit from the standard atomic and declare a new copy constructor so that you can actually copy it? This is getting a little bit into crazy territory, it feels to me, because the atomic operations are extremely simple in the first place. So it's better to just make a new class that does what you want. If I had to guess, I would say that the reason why the API was designed this way is because there was a decision that as a template class, an atomic should be able to use anything as a template argument, including some complex structures and classes. I guess it's then hard to decide how one of those complex classes could be copied atomically, and so they say it's just not possible. Or perhaps it's because then in order to guarantee atomic access to one of these more complex things, they use a mutex, which is a higher level operating system primitive. And mutexes can't be natively copied. They need to be initialized through operating system calls. And so they transitively applied that limitation to the atomic, despite an atomic being much simpler in concept. When it comes down to it, if you're starting to use atomic variables, presumably you are trying to make some low-level performant code. But this makes the opposite assumption. Another problem with the API is that they don't make any assumptions about what the underlying memory model or computer architecture are. The result of this is that they target something that's very general, and they target the safest possible option. Namely, they target sequentially consistent as the default memory model. This has some sort of logical basis in it, but the problem is that no computer is actually sequentially consistent, including x86, which is probably the main target, and definitely ARM is even weaker. So for any of the common computer architectures to actually implement sequentially consistent memory stores and loads, you need to impose some extra overhead. Because this is the default behavior, you either have something that is relatively concise code but has poor performance, or you have to constantly specify a weaker memory ordering, and that is then extremely verbose because every single access has to be tagged with, oh, I want to do a relaxed loader store. My final complaint is more of a stylistic one than an actual technical complaint. I don't like that atomics behave so similarly to normal variables. There's nothing really to distinguish them because there's operator overloads of equals and plus plus, for example, to do an assignment or an increment. The thing is that when I'm doing operations on an atomic, I need to think about those, and those should stand out in the code because that's going to be a communication overhead, and the atomics are going to be an order of magnitude slower from any other memory access. So then if you're designing a new API, that raises the question, if atomics are operations instead of something about the memory itself, does it make sense to actually use a struct, or should all of the operations simply be functions? I think it's still useful to have structs for a couple of different reasons. When it comes down to it, these reasons are mostly stylistic, but I like being able to see if I put an atomic somewhere, oh, that's the semantic. This is an atomic variable. And I then like being able to see the methods that operate on that value. In my code, I also tend to make a differentiation between something that is intended to be signaled through, which I will then call an atomic, versus more like payload data that the signal is indicating is ready. And that payload data I would more likely call then volatile, to indicate that it's there, it needs to be read and written from, but that's not the key mechanism for signaling. As I mentioned earlier, I also like the idea of explicit load, store, and methods like that, as opposed to operator overloading, because that again makes the signals stand out in the code more easily. Okay, so with all of that talking out of the way, here is the entire implementation of an atomic integer. First, there are a couple of basic constructors. Then I have the load and store methods. These are really just reading and writing memory. They provide the same guarantees that x86 provides. And if you notice, there's these read-write barriers. So those are the compiler fences I had mentioned earlier. For safety, I put a read-write barrier before and after each of the loads and stores. To reiterate, these don't actually turn into any instructions at all. They simply prevent the loads and stores from being reordered with other code. Finally, I implement a couple of atomic operations, namely fetch add and compare exchange, and those are done simply by using the operating system level primitive that's provided. Those in turn, I think, are just macros that emit an x86 instruction. Finally, as you can see, the atomic value itself is marked as volatile to force the reads and writes to actually be done to it. And that's all. That's the entire implementation. Next, I'll talk about how to implement a spin lock. This is again a case where API design can induce performance problems, and there's a trade-off between convenience and performance. The API design influence on this is a bit funny in this case, because generally it seems like APIs don't provide a spin lock. So it's not even an option. You can't use it, you have to make your own. Instead, APIs generally provide a mutex. And the difference between a spin lock and a mutex is perhaps a little subtle. In the way that you use it, it's pretty much the same. You say, I want to lock it. I want to unlock it. The difference is that a mutex is an operating system level primitive, whereas a spin lock is entirely in user space and doesn't involve the operating system at all. Generally, libraries only provide a mutex because, well, it's a good default, and it's the don't shoot yourself in the foot option. If you don't feel confident in when you should choose one or another, or if you have a single global resource that you need to have exclusive control over by a single thread at a time, then you should use a mutex. There are a lot of good things about mutexes. As a fast path, most will spin briefly before they actually go to calling the kernel, so the fast path is actually fast. And because it's an operating system level lock, it will put a thread to sleep if it's waiting for too long. This allows other threads to run and frees up resources. And if there's multiple threads that are contending for the lock, a thread will remove itself out of the way and allow other threads to complete their work so that they can get done with the mutex. This prevents starvation of threads. Also, since the operating system knows what threads were put to sleep to wait for the mutex, it can wake a single thread when it's ready and the mutex has become free. So that's a lot of good properties of mutex. Why would you not want to use one? Probably the biggest problem is that a mutex isn't easily copyable. It has operating system resources and needs operating system calls to create and destroy a mutex. And that doesn't work so well if you need fine-grained control over memory resources, like every element in an array. Operating system calls to create and destroy mutexes are slow, and it may potentially take resources in the operating system itself to keep track of these things. So I don't know what the implication is of having thousands, tens of thousands of mutexes. It might potentially be bad. So what about a spin lock? Basically, the benefits and drawbacks are the mirror of a mutex. You can waste computer resources. You're prone to self-starvation or starving threads from other processes. This can especially be a problem if you have more threads than you have logical processors. Particularly problematic if you increase the priority of your threads, you're potentially starving drivers and important system functions from being able to run. Spin locks are generally bad in high contention scenarios. So ideally, you only use them if you are expecting that you are not going to have to wait for the lock, and you should do as little work inside of the lock as you can to exit it as quickly as possible. This is also true for mutexes, but it's more important for a spin lock. Also, a poor implementation of a spin lock can cause a lot of memory bus traffic and degrade overall performance of other threads as well. However, the good thing about them is you can have lots of them. In fact, it's better to have lots of spin locks instead of a few of them, because that's going to generally reduce the contention over any given lock. They don't take much memory. It's just an integer that you can stick anywhere you want. And they also have the potential to be really fast. They're simple and can have the minimum latency possible. These good properties exactly match my requirements for speeding up the train simulation, so I made a spin lock. Again, the implementation is extremely simple and short, but there's some thought that needs to be put into it. What you can see is to acquire the lock, you do a compare exchange operation. If that succeeds, then the function simply exits. If it fails, then I loop doing non-atomic operations to read the value, and whenever that's not succeeding, I emit a pause instruction. This basically tells the CPU to do no operations for a short period of time. In theory, this steps out of the way of any threads that are running on the other logical processor in the core and burns less power. Just to get it out of the way, there's another possible implementation, and this is something that was suggested by the AMD developer relations team. This uses what's called the test and set method, where you first try a non-atomic operation to load the value. If that succeeds, then you try the compare exchange. This is basically the same idea, except it's the reverse order. You first do a cheap non-atomic operation before trying the atomic operation that is more expensive. This is also fine. I don't think it really matters too much which one you use, but this is going to be slightly slower in the fast path because you're doing an extra load operation. And the goal is that you should generally be in the fast path anyway. So, In my profiling, I actually couldn't distinguish any difference in speed between them. So I left an if-def to select which one to use, and if I run into problems, I can try switching over. This finally brings us to the meat of the problem, the big one, the parallel for statement. How do I implement that? Again, before talking about the actual implementation, I need to talk about the API and how bad API induces performance problems and the trade-off between convenience and performance. I know, I'm starting to sound like a broken record at this point. The first thing that I need to do is look at the nature of the parallel computations in my program. The basic thing to notice is that the game simulation is bursty. What this means is that in a given frame, there's some amount of time that is spent doing the simulations, and then the rest of the frame, the CPU is basically idle. There's some amount of work done doing drawing and stuff like that, but that's single-threaded and isn't all that computationally intensive either. When running the simulation, the player can choose how many iterations should be run per frame. And so oftentimes, if you want to see something that's simulating at a reasonable, observable speed, the time spent doing a simulation is extremely short. And only when you're doing really fast simulation, where you're running 1,000 simulation ticks per frame, then the performance can start to become a real problem. Each iteration, however, has extremely short duration workloads. So when you're doing the simulation, you need to have the absolute lowest possible latency for distributing your work. The way that I deal with this type of computational pattern is to have explicit wake and sleeping calls. So before I'm going to be doing parallel work, I call a wake function to put the threads that are going to be doing work into a high power, low latency, busy wait, where they're burning cycles to pull work off as fast as possible. Depending on the type of workload, I can choose to wake different numbers of cores. If there's something that's more throughput sensitive, then I can wake all of the cores. If it's latency sensitive, then I'll just wake the low latency cluster of cores. Then, as soon as the parallel work is done, I can tell the threads to go to sleep to relinquish processing power to other processes that may be wanting to run, or if there's nothing running, then simply not to be burning power for no reason. Again, since I know exactly when I have finished my parallel work, I can put the threads to sleep immediately. So let's take a look at how some other existing libraries handle this. OpenMP implicitly wakes and puts threads to sleep. Looking at profiles, it seems to put threads into a busy wait state, somewhat akin to how I do. And the difference is because it doesn't know when threads are going to be done with their workloads, it continues to busy wait with a timeout of 200 milliseconds. The CRT PPL library is also implicit, but takes a somewhat different approach in that it puts threads to sleep very quickly. The problem here is basically the opposite, which is that instead of burning power, you're potentially going to have large overhead because you're excessively putting threads to sleep and waking them up. Both of these libraries seem to try to play nice with the operating system by calling yield, which yields control to the operating system scheduler to try and put another thread in their place. The problem here is that the libraries don't have any explicit knowledge of when the work is actually done or not, so they call yield when it's not necessarily a good thing to do it in the middle of workloads. Operating system calls like yield are generally slow, so that's going to be a performance problem. As well, once you ask the thread scheduler to step in, there's a chance that it's going to move your thread to a different core. This is extremely bad for performance because when you move to a different physical core, you're going to lose all of your cached data. Calling yield like this isn't a good solution because it doesn't address the fundamental problem. If you want to play nice and share computational resources with other threads, there's already a hardware solution for doing that, namely hyperthreads. If you think that this is going to be an issue, what you can do is put one thread per core and leave the other hyperthread logical core unused by your process, and then the operating system can put other threads from other processes on those logical processors, and the hardware will more fairly and in a more fine-grained way split the computational resources between those logical processors. This brings us to what is somewhere between an API interface versus an implementation detail. I assume that because this is for a game, that the game is going to have the user's primary focus and attention, and then other processes are mostly background tasks. With that in mind, I pin threads to the cores. I then have 4 different classes of waking states depending on how I'm going to be using the CPU. The simplest case is running single-threaded, and this is a synonym for the sleeping state. In this case, I set the thread's priority to highest and pin it to core 0. Note that I pin it to the actual physical core, not to a particular logical processor. This means that if you have 2 hyperthreads, that it can run on either one of those processors. Highest is an elevated priority, but it's still in the realm of normal user space thread priorities, so it's not going to be higher than critical system processes. The next is cluster of cores, as described in my earlier discussion of architecture, and these are also set to a highest priority. And this is then going to be the set of cores that have the lowest latency communication between each other. Again, this is setting 1 thread per physical core, and that will typically mean that each thread has a choice of 2 logical processors. Next up is big cores, and that is simply setting the threads to run on any of the physical cores, but only 1 thread per core. The additional threads that come with this have above normal priority, which is less than highest. As I start using more threads, I'm going to continually decrease the priority of the new threads that I add. This is in recognition that as I'm using more of the computational resources available, that there's going to be more contention over them, and I need to step out of the way sometimes for other processes to run. Still, at this point on a normal CPU, I'm going to be using half or less than half of the logical processors. The final waking state is all processors, which will put a number of threads equal to the number of logical processors into a waking state. All of these remaining threads are put at thread priority normal so that I don't completely take over the CPU and let nothing else run. In the case of an Intel processor, the cluster of cores and big cores are actually the same set of processors. And as I had described earlier in this video, I determine all of this cluster information from the Windows API get logical processor information that returns the cache and processor masks for all of the CPU components. Another design choice is how you specify the callback function. At first, I had used the standard function as a callback, which is able to accept a function or a lambda function. But I discovered eventually that this is actually quite slow. The problem is that the standard function takes 64 bytes, which is exactly a cache line. This means that any other information that I'm going to transmit besides what function to call takes more than one cache line in total. This wound up actually then doubling the amount of time it takes to send a request to worker threads. Instead, what turns out to be better is to use a raw function pointer. This is somewhat less convenient because you can't use lambda captures. You have to cast pointers of void data that's being passed in, but it winds up taking only a pointer width for the function and a pointer width for the void data that you want to pass in, which is a total of 16 bytes. This leaves a total of 48 extra bytes in a cache line that can be sent along to the worker thread. I hadn't realized this beforehand, but it turns out that if you have a lambda function that doesn't capture any variables, it will actually automatically decay to a function pointer. So you can still have the convenience of a lambda function just without all of the features. Another difference between my library and other parallel libraries like PPL is how the indices are passed to the callback function. In most libraries, the callback function takes an index. In mine, the callback takes a range. This is important because it allows you to write setup and teardown code before and after the loop, which may be important. It also allows the compiler to do a lot of optimizations over a loop, which wouldn't be possible through an opaque function pointer. There are lots of different possible optimizations. Some of those are lofting computations to be outside of the loop, doing strength reductions, for example, converting multiplies into additions over the loop, and auto-vectorization. Another concern is that calling a function is not free and is just, in fact, more expensive than doing a loop. Whenever you call a function, there's a preamble and postamble of setting up and tearing down the stack frame and also passing any arguments to the function. Finally, it's important to have some sort of mechanism for specifying the thread ID. And this is simply the idea of having the index from 0 to n of which thread the work is running on. This can be useful for accessing scratch memory. For writing outputs, they're generated per thread, for example, command lists in Direct3D, or for performing reductions. I'm sure that there are other use cases as well, and it's just a nice thing to know. OpenMP provides the thread ID, but for some reason PPL does not. And this limits the type of computations that you can do with PPL. In my API, the thread ID is simply an index that's passed into the function when it's called. Okay, so let's put this all together into an example. Suppose that I have a serial implementation of calculating the sum of values in an array, and I'd like to parallelize it. Here's an implementation of that parallel sum using my threading library. You can see that before any work is done, I first need to make sure that the threads are awake by calling parallel.wakeAll. And at the end, I put the threads to sleep. Following that, I then define the per thread sum as a struct that contains a value. And the key thing to notice here is that I've set that to be one cache line in length so that the different threads will write to different cache lines and not contend with each other. Following that, I have the sum data struct, and this contains the values that will be passed to threads through the void data pointer. In particular, this contains the values that will be summed over, and then an array of the results per thread that thread has summed up. You can then see that I request the threading library to equally partition the data between the different threads. Each thread calculates the sum of the values in its range and stores the result into the thread sums array indexed by the thread ID. Finally, the sum of thread sums is calculated, which gives the total sum. If you like what you've seen so far, go ahead and hit that like button. Okay, so now that I've talked about the API for the Parallel 4, how did I actually go about implementing it? As it turns out, the implementation actually doesn't require all that much code. In total, the header was 204 lines, which includes the atomic and spin lock implementations, and the CPP file was 502 lines, a large part of which was just finding and printing the CPU clusters rather than the actual work distribution logic. This is literally the number of lines in the file, which includes empty lines, comments, brackets, and boilerplate code. Although the total amount of code wasn't that much, there was a lot of iterating and profiling and improvement that happened. Also, in the process of making this video, that forced me to think through the code carefully and wound up making it significantly faster when I rechecked my assumptions. At its core, distributing work amongst multiple processors is really a communications problem. Naturally, this is defined in large part by the data that's actually being sent between the processors. When designing the communication, there's a couple of things to keep in mind. One is that you should treat cache lines as a packet of data that's sent over a network, because in the end, that's exactly what it is. You also want to minimize the number of threads that are reading or writing from the same cache line. So long as all of the data fits within a cache line, if you duplicate it, then it's worth it to duplicate it if that reduces contention. For me, this was the case where duplicating the function pointer and data that's passed to the threads was more efficient than having the data in one place and accessed by multiple threads. Conversely, if you're going to spill over into a second cache line, you want to do everything you can to reduce your data to fit into a single cache line. And the example I gave before of using a function pointer instead of a standard function data structure is this case. Finally, it's important to write data in bursts. The exclusive locking of cache lines happens entirely implicitly in the computer architecture, and you have a worker thread that's trying to pull the data at the same time that the controller thread is trying to write the data. Whenever the worker thread tries to read a cache line, that makes the cache line state change from an exclusively checked out writable mode from the main thread into a shared state where the worker thread is able to read it. So if the main thread is slowly writing a byte of data every once in a while, and the worker thread is constantly reading it, then the cache line state is constantly changing between exclusively locked versus shared versus locked again when a write happens again, and that's very slow. So instead, the main thread should prepare all of the things that it wants to write, and then write them all at basically the same time to avoid this detrimental behavior. Okay, so here are the actual data structures that I use. You can see that there's two. There's the parallel thread control and the parallel shared control. The thread control contains the data per thread and is mostly used as a way for the main thread to communicate information to a worker thread. The first variable, job count completion, is the only variable that is actually updated by the thread itself. Once all of the other values are set by the main thread will increment job count creation to indicate the worker thread should actually start running the job. Now let's take a look at the shared control. When worker threads finish their job, they'll increment the num workers finished. When that reaches the number of workers, then the main thread knows that the workers have all completed and can continue. Also, in the case of dynamic work distribution, the worker threads all need to communicate through the atomic variables for the dynamic work. The code for the worker thread is actually so simple and straightforward that I can show it here on one page. Basically, the thread is sitting in a busy wait until the job count is incremented by the main thread. If there's work to do, then the worker thread will look at the control state to determine what type of work to do, and will then do it. Something to point out here, I suppose, is that going to sleep and terminating are considered types of jobs. Also, just reading the flag for if there's work to be done or not doesn't require an atomic read, modify, write or anything like that. It's just reading the value from memory. Partitioning the data between threads is really simple. It just gives each thread its full range. The case of dynamic distribution of work is slightly more complicated, but really not all that complicated. Threads communicate through a shared data structure. Whenever a thread finishes the work that it's currently doing, it needs to reserve a new chunk of work to work on. All of the threads do this repeatedly until all of the work is completed, in which case the threads quit. Reserving work is done through simply incrementing an atomic counter. The code I show here is the simpler special case when the work item size is 1. But it's easy enough to imagine how you'd extend this for larger chunks. So great, that's the worker thread. How do you actually launch work on a worker thread though? When there's a new job, the main thread will first set the number of workers finished to be 0. It then sets the control structure of all the threads that will run and bumps the job count creation to trigger that thread to run. At this point, the worker threads are off to the races, and the main thread can join in to do its share of the work. After the main thread finishes its work, then it needs to wait for all of the workers to also finish, which it determines by checking the number of workers finished atomic variable. Putting threads to sleep and waking them up is done through a single function that's passed in the target waking state. To reiterate from before, I have 4 different waking states. There's a single thread being awake, a cluster of cores, the big cores, or all threads. When I say that a thread is asleep, it means that it's waiting on a semaphore. A semaphore is an operating system primitive where when a thread is waiting on a semaphore, the operating system is free to schedule other threads in its place. Whenever the semaphore is signaled, then the thread will wake up and will continue execution from that location. A semaphore can actually be used to signal multiple threads at the same time, and this is more efficient than having a ton of different semaphores. So the way I organize things is that I have one semaphore per waking state, excluding the single thread state because the main thread always has to run. By grouping the threads like this, I need to make fewer calls to the operating system to wake the threads. The basic idea behind the sleeping-waking function is that it knows the current waking state and it knows the target waking state. Based on that difference, it can determine which groups need to go to sleep or wake up. So first, all of the thread groups that need to go to sleep are put to sleep, and then all of the thread groups that need to wake up are woken up. It's important to note here that there's a potential race condition, and so the waking threads are actually told to run an empty function so that the main thread can then create a barrier to wait for them all to finish waking up. Initializing the parallel library is actually the longest function of all of them. This is due in large part to the analysis of what threads should be run on which cores and what the clusters are, etc. There's also various setup stuff that needs to be done. For example, creating the semaphores, starting the threads, and setting the affinity of the threads to particular cores and the priorities of the threads. Honestly, it's not that much code, and more speaks to how little code everything else requires. And finally, termination is also fairly simple. Whenever you want to shut down the library, first you need to wake all of the threads and put them into the terminate control state. The main thread then waits for all of the threads to finish, at which point it can kill the threads via the OS, and it can then destroy all of the semaphores. And at this point, I've described basically the full implementation. Finally, we can run some benchmarks to figure out how much overhead is involved in the different operations. The first thing that we can test is how much overhead is involved in simply waking up and sleeping the threads. This gives an indication of, if the threads are all asleep, how much work do you have to do in order for it to be worthwhile to wake threads. Here you can see that on my computer, the 2600X, that the overhead for waking a cluster of threads is about 2.3 microseconds. For waking one thread per core, that takes about 6.5 microseconds, whereas waking up all of the threads on all of the logical processors takes about 14.5 microseconds. My friend with a newer Intel chip also ran the benchmark on his computer, and there you can see that waking one thread per big core takes almost 11 microseconds, and waking all of the threads on all of the cores, which also includes the little cores, takes about 53 microseconds. As I had mentioned earlier in my discussion about the implementation, this is measuring the amount of time to signal through a semaphore. Now let's take a look at if we have some actual work to do. The first thing I'm going to look at is the amount of time it takes to complete the work when statically partitioned across the processors. For this test, I want the threads to do some mathematical work that just occupies them. The test function basically just does some trigonometric operation. In order to ensure that the compiler actually does the function, I have it write its results to a value in memory. I also make sure that those memory locations are on separate cache lines for the different threads. Here I show what my test function looks like. For different APIs, this needs to be done a little bit differently. In OpenMP, it uses compiler pragma directives in order to tell the compiler to parallelize that loop. As I had mentioned before, OpenMP will do a busy wait for 200 milliseconds, so after I tell it to do work, I put the main thread to sleep to wait for all of the worker threads to also go to sleep. Finally, with PPL, we run into the issue that it doesn't provide a thread ID. In this case, I can get the effect that I want to achieve by using a thread local variable. I really don't like thread local as a language construct very much, but I don't really have an alternative in this case. Here are the times measured in milliseconds to complete a fixed amount of work in some different configurations. For both processors, the smallest amount of work shown at top is the number of items equal to the number of cores in a cluster. I'll mostly look at the timings for my processor. You can see that for 3 items, my code runs about 7 times faster than OpenMP and 6 times faster than PPL. In this case, the overhead for OpenMP looks worse than for PPL, although that's generally not the case. The thing is that OpenMP sends a message to every thread, whereas PPL only sends a message to the threads that are actually going to do work, because there's fewer work items than there are cores in the computer. If you then look at 12 items, which is equal to the number of logical processors in the computer, then you can see that OpenMP is only 5 times slower than my code, and PPL is now 19 times slower than my code. In this case, all of the libraries are sending a message to all of the threads in the system, so you can finally see what is actually the overhead per thread. This is the minimum amount of work that you can have a processor do, and is therefore dominated by the overhead of sending a message to a thread to tell it to start, and the thread then communicating when it's done. With the small test size, we now have enough information to actually calculate how much overhead there is in starting one of these jobs. As you may recall from far earlier in the video, when I was talking about the communication latency between the cores, I said that the minimum theoretical amount of overhead would be 169 cycles. This is because we're sending 2 messages to and from a core, and there's a 22.8 nanosecond measured average latency when measured at 3.7 gigahertz. From a serial benchmark, I know that each test item takes on average 53.8 cycles, and that the entire serial run took 1,501 milliseconds wall clock time. When running on a cluster of cores, there are 3 threads that are running in parallel, and the total amount of wall clock time to complete the work was 5,054 milliseconds when running in parallel. If we take the serial time divided by 3, then that's the amount of time that it takes to actually do the work per parallel thread. Thus, the amount of time that a parallel thread does stuff that isn't productive work is going to be the total running time, which was 50,054 milliseconds, minus the amount of time that that thread was doing useful work, 1,501 divided by 3 milliseconds. Dividing that by the serial time gives us the ratio of overhead to actual useful work per item. Multiplying by the number of clock cycles to do an item of work then gives us the amount of overhead in cycles on average to run a parallel loop. This comes out to 163 cycles on average. Accounting for measurement error from various different sources, this basically gives exactly the expected theoretical value. So basically, job well done. In the limit of a large amount of work, I also outperform OpenMP and PPL by 1.4 and 1.2 times respectively. Here, the overhead is determined by things other than the starting and stopping overheads, but rather some sort of persistent factor. In both OpenMP and PPL, when I look at a profile, I see that threads are spending time in sleeping or yielding. So my assumption is that when they have some work items complete and control comes back to the threading library, that they set the threads to yield. What this means is relinquishing control of the processor back to the operating system to allow the operating system to try scheduling some other threads. These other libraries also don't pin the threads to processors, and so the threads can migrate between cores and will especially attempt to do migrations during these yield calls. Here's a capture of an OpenMP run, and the green part means that the threads are executing as normal. The blue means that the threads are sleeping, and you can see that there are these periodic increases in the sleeping/yielding. Every once in a while, for reasons that aren't quite clear, the performance tanks, and it seems like the threads are all spending a lot of time sleeping or yielding, and I'm not quite sure why this happens. In PPL, you can see that it has a somewhat similar pattern of periodically having threads yield. But in PPL, you also have the opportunity for random performance drops when the threads all go to sleep. This is because PPL is much more aggressive about putting threads to sleep rather than busy waiting like OpenMP does. By putting threads to sleep, I mean these red regions where the threads are synchronizing on a semaphore, for example, waiting for the threading library to tell them to do some work. Instead of statically partitioning work, sometimes it's good to dynamically distribute the work. And so I have a benchmark measuring that. Here I only compare against OpenMP, but I assume that PPL would be even worse, or no better. When dynamically partitioning data, you have an option of choosing how much work each thread should take each time. Here I compare increasing chunk sizes from the smallest possible, which is 1 item of data, to 16, and then 256 items per chunk. Here we can see that the cluster of cores doesn't perform all that well, and that because this is basically just running a big job where the cores are taking a piece at a time, naturally it makes sense to use more cores. Thus, if we compare when using all threads in my implementation versus OpenMP, you can see that my implementation outperforms OpenMP for all of the different chunk sizes. As a reminder, getting a chunk of work involves incrementing an atomic variable. Incrementing a variable requires one memory transaction at most. If a processor already has exclusive access to a cache line, then it doesn't need to do anything and it can just write the data. However, if the cache line is owned by a different core, then it requires a memory transaction to get the ownership of that cache line and then to do the write. Again, if we look at the theoretical overhead of one memory transaction, that would be 22.8 nanoseconds times the 3.7 gigahertz, yielding 84 cycles. The actual measured overhead was 63.9 cycles, which is actually lower than the theoretical single transaction. So that indicates that we're not doing a memory transaction every time that we're grabbing a piece of work. Whew! So that was a really long technical video, so I hope that you stuck around through to the end. What I hope that I've managed to show is that it's important to understand some of the architectural details if you're going to try to write performant code. Also, if you're designing for a specific application or use case, that you can often outperform existing off-the-shelf libraries. It's also important to consider the API design because the decisions that you make in your interface will determine sometimes the performance characteristics of your code. Sometimes they're just plain bad design choices. Other times there's a trade-off between speed and convenience, and you need to choose which one you care more about. In my design, low latency was of utmost importance and overrode any other considerations. I only needed parallel for loops, and so that's the only thing I implemented. I don't know how difficult it would be to implement something more general, and that may potentially come with some performance trade-offs. I also don't support fancy things like calling parallel for loops within parallel for loops. A lot of games look to Jobify and parallelize their entire code base, but I was really mainly looking at just making the simulation parallel and then a few other type of utility functions. But the rest of the code was honestly fast enough, and I don't need to make other things parallel. If you have any questions for me, go ahead and leave a comment below. If you liked the video, then it's never too late to subscribe, and you can feel free to check out some other videos on my channel. Have a great day.